Hello everyone, and congratulations to everyone in the audience for having the acumen to stay for what is going to be a fabulous session chaired by Jamie Cleverly on net carbon and sequestration. Thank you.
Hello everyone, thank you for making it to the end of the conference. Just like Beryl said, we're now going to listen to 3 talks on a topic that's become very important and in the industry sector on sequestration of carbon, particularly in soil. So I would like to welcome Lucas Cernusak to open the session.
Okay, thanks Jamie and Beryl, and thanks to everyone for hanging in until the last session. Okay, so my name's Lucas Cernusak. I'm a plant physiologist. I work at James Cook University in Cairns, and I would like to talk to you about tropical tree responses to elevated CO2. So, as a little bit of background, there are a couple things that we know are very consistent responses of plants to a higher CO2 concentration. One of those is an increased rate of photosynthesis. So carbon dioxide is the substrate for photosynthesis. When we raise the CO2 concentration outside the leaf, it also increases inside the leaf. The enzymes that are doing photosynthesis go faster. And you can see an example here of a leaf exposed to different CO2 concentrations. So this is the short-term response. Of course, the pre-industrial CO2 concentration was about 280 parts per million. We're about 420 today and increasing. And the other very consistent response is an increase in the water use efficiency. So that's the amount of carbon dioxide taken up for a given amount of water lost to the atmosphere. And this is, in fact, the most consistent response that we observe in elevated CO2 experiments. And I've picked out a particular example here to show that, because these are, this is water use efficiency measured in tropical tree rings across 3 continents, so Africa, South America, and Asia. And you can see the top panel of graphs are increasing CO2 concentration inside the leaf. The middle are the increase in water use efficiency. And then the really interesting thing here that I want to talk about is that there's not an increased growth rate of the stems. So the diameter increment, the diameter growth inferred from the tree rings did not increase. It's a really surprising result because we know photosynthesis goes up, and we would expect that should drive a faster growth rate. So this is the paper that those graphs were from is by colleagues in the Netherlands. No growth stimulation of tropical trees by 150 years of CO2 fertilization, but water use efficiency increased. And I wrote a news and views that went along with this, and basically discussing this sort of surprising result. It's a bit of a puzzle. Why don't we see increasing growth rates? So I want to use some results from an experiment that I worked on with colleagues at the Smithsonian Tropical Research Institute to try to inform that question. So this is my longtime collaborator, Klaus Winter, in Panama at the Smithsonian. He has this nice setup with 9 of these geodesic domes, glass domes, and so we can have a nicely replicated experiment. So we have half the chambers with elevated CO2. We had 2 times the ambient concentration, so 800 parts per million, and half with 400 parts per million. And then I was also joined in this by Martijn Slot, who you can see making measurements inside the chamber there. So I want to also explain that photosynthesis consists of 2 kind of distinct sets of reactions. There's the light harvesting reactions where energy is absorbed, and that results in electron transport and eventually passes energy to the carboxylation reactions in the form of ATP and NADPH. And these are truly distinct sets of reactions. They have surprisingly different temperature responses, for example, and they also have different responses to CO2. And I'll show you in the next couple of slides why I think that's really important and an important thing to understand. So this is the model of photosynthesis. This is a famous model invented by Graham Farquhar, Susanna van Kemmerer, and Joe Barry. And here you can see actually three sets of reactions here, but focus on the Rubisco limited and the RUBP regeneration limited. So Rubisco is carboxylation, RUBP regeneration is electron transport. And notice that, that their CO2 responses are different. And so the leaf has a job of investing in those two sets of reactions, building the machinery in such a way, optimally, if it does it optimally, that they both co-limit, equally co-limit photosynthesis. And so we can see in this picture that dot where they cross over, the CI transition point, is where if we're moving up in the CO2 concentration across the x-axis, that's where the limitation passes from the electron transport, from the carboxylation limitation to the electron transport limitation. So there are really sound reasons for expecting that plants will balance these reactions in such a way that that CI transition point should be near to the operating CI. And CI is the CO2 concentration inside the leaf. So what happens then if we raise the CO2 concentration outside the leaf? That also raises the CO2 concentration inside the leaf. And then we think that the plant should adjust its investment in electron transport and carboxylation so that that CI transition point shifts up. But the way it makes that adjustment is what's really important. So the adjustment, we refer to it as acclimation. And you can see on the left-hand side, if it adjusts the CI transition point by changing the carboxylation, the VC max, then that solid line is the increase in photosynthesis. And as we go to higher concentrations, it actually flattens off a lot compared to the lower concentrations. On the other hand, the right-hand graph shows what would happen if it instead adjusted the CI transition by changing the electron transport rate, the Jmax. And you could see that would result in a much steeper increase in photosynthesis than if the adjustment was made by changing VC max. So this, I think, is a really important and interesting question. Okay, so I want to give one other little bit of background, which is about water use efficiency. You see an equation in the upper left. It's just a simple rearrangement of a fixed law description of photosynthesis, a diffusion equation. And the left-hand side is the intrinsic water use efficiency, photosynthesis divided by stomatal conductance. And then we can see in the numerator a term CI over CA. It turns out if this stays constant, the ratio of intercellular to ambient CO2 concentrations, then if CA goes up, that water use efficiency will increase in direct proportion to the increase in CO2 concentration outside the leaf, the CA. So this is how we get the big increase in water use efficiency. We find that plants do tend to keep this CI over CA constant. You can see that from the tree rings in the graph on the bottom. So over the last 150 years, as the CO2 concentration increased from less than 300 to close to 400 parts per million, that CI to CA ratio remains constant on average, and the right-hand side graph shows how that leads to a big increase in water use efficiency, a steadily increasing water use efficiency. Okay, so the questions then are, does investment in Jmax and VCmax acclimate under elevated CO2? Which of the two components of the photosynthetic process get adjusted to drive that acclimation? And can understanding that give some insight into why we might see a lesser increase in photosynthesis and a same large increase in water use efficiency? We measured CO2 response curves. We used this nice R package from Remco Dersma to fit the model to the curves. And here's some results. So you see here the gas exchange photosynthesis. So the trees in the domes at 800 parts per million, they do have higher photosynthesis. It's not that much higher. So that's really the point of the talk. Stomatal conductance decreased a little bit. That's also expected for angiosperms. Importantly, that CI over CA, it remains the same. It's unchanged. Therefore, water use efficiency is going to be approximately twice as high in the elevated CO2. And then here's those measurements of the different parts of the photosynthesis process. You can see the CI transition did increase, indeed increased, so the leaves adjusted to the higher CO2 concentration. They rearranged their investment in those two different components of photosynthesis. Which did they change the most? They changed the VC-max. So they down-regulated VC-max. That means the increase in photosynthesis is much less than if they had upregulated J-max in order to shift that transition point. So those results, photosynthesis increased from 17 to 22 micromole of CO2 per square meter per second, an increase of 28%. For a doubling of CO2, that's a much lesser increase than if there were no acclimation of VC-max and J-max. CI transition increased. This is good evidence for our theoretical understanding of acclimation. And that acclimation took place through a change in VC-max. So a 25% decrease in VC-max. Getting to the water use efficiency, here you see on the left that constant CI over CA, and then on the right-hand panels, a big increase in water use efficiency, whether it's expressed as photosynthesis over stomatal conductance or whether it's photosynthesis over transpiration, actual CO2 taken up per unit of water lost. So these results would tend to support this idea that tropical trees, when exposed to higher CO2 concentrations, indeed their water use efficiency increases, but they don't actually grow in water-limited environments that much. Some do. So CI transition increased. It increased through reduction of VC-max. CI, CA remained constant, therefore water use efficiency increased. And I think this gives some really good insight into why we don't see large growth responses of tropical trees. They acclimate in such a way that the increase in photosynthesis is less than it would otherwise be with a higher CO2 concentration. They still get the big increase in water use efficiency, and I think this gives us some grounds for predicting where we might see increasing tropical tree growth. It should be in water-limited environments. It probably should be where the tropical rainforest in Australia, for example, meets the tropical savanna. We should see expansion of rainforests there, benefiting from the higher water use efficiency, but probably not in non-water limited interior wet tropical forests. Okay, thanks very much.
Okay, g'day. Thank you for staying this afternoon. This has been my first experience of TERN, and I've quite enjoyed the whole breadth of topics over the last 2 days. My topic is not on carbon, despite me being in this session. I'm talking about the development of new instrumentation for measuring water vapor fluxes that is of a comparable accuracy to eddy covariance, but about 80% less cost. I'm an agricultural engineer. My personal areas of interest are evapotranspiration measurement and modelling, and developing instrumentation to measure that. And I've currently got a postdoc to continue on that work for my PhD. Oh, beg your pardon. I work at the Centre for Ag Engineering up in Toowoomba, and most of our work is done in broadacre cropping. such as these sites here, we're mainly funded by the cotton, sugar, and dairy industries. These are industries that have a relatively small geographical coverage, but they have very large environmental impacts, especially in terms of water consumption, nitrogen, carbon, chemical use. These industries are very aware of that, and they're working hard to try and fix those problems. And they're pouring millions, even tens of millions of dollars per year into fixing these problems. And that's where we come in. We're employed to help them with solving their water use problems. In a lot of our work that we do with them to improve their irrigation efficiencies, we have a need to demonstrate that the technologies and practices that we develop actually do deliver improved water use efficiency. In years past, we'd always used eddy covariance as one of the tools, and it worked well, but to be honest, it was a pain in the butt because we would have to set it up in the middle of these cropping fields, take it down every time they had to bring machinery through, which could be 6, 7, 8 times per season. You can't just ask the farmer to do that for you, it's too complex. Not only that, it's expensive. It requires post-processing usually. It's very hard to integrate into a real-time monitoring and control system. So we looked for other options. Lysimetry is not an option for us because they have to be able to cultivate through the field, so we can't have a permanent installation. We can use Penman Monteith and other models, but then you start introducing some pretty big uncertainties around crop factors, stress factors, even just measuring ET0 accurately. So one of the options that came up was using BREB, bone ratio energy balance, which was a technique that was first proposed about 100 years ago. In recent decades, it's fallen by the wayside because eddy covariance has been very enthusiastically adopted. But we went back to BREB as a technological option that could give us some really good quality water vapor fluxes. If you're familiar with the idea of BREB, you may have seen some systems like these. BREB usually consists of a set of temperature and vapor pressure sensors that you measure at 2 heights above a crop or some sort of ground surface. These are traditionally what you'd see, and you'd be measuring vapor pressure and temperature, and from that you would be determining the T/E gradients, and that would go into your calculations to determine the Bowen ratio, and from that you would be able to calculate your evaporation. There is another method though that's widely unknown, and this is called what I call the profile approach. It was around a little bit in the 60s and 70s, but the instrumentation limitations at the time meant that it really quickly fell out of favour. But I decided to give this a new burst of life. So I built my own, I prototyped this 5-height profile BREB system. So rather than just using 2 heights above a surface, you've got 5. And then, and these are some photos of my gear that I built. You might say, well, why have 5 heights when 2 sounds a lot cheaper and a lot simpler? The reason is because, unlike the 2 heights, the 2-height system, because you're dealing with very fine increments of temperature and vapor pressure, there's always a need to alternate the positions of the sensors to cancel out inherent sensor biases and errors. With the 5-height system, you treat every sensor as producing a pseudo-random error. You fit a line through it, and you can get your T/E gradient through that way. So this way, you don't have to have any moving parts. You also don't have to allow sensors to adjust to their new atmosphere every time you rotate them. It's got lower power demands. So this is, like I said, it's been done before in the history. These are a couple of examples from the literature. The one on the left, that team measured at 10 heights. The one on the right, these guys from Russia did it at 5 heights, and they were getting really good results. But the instrumentation that they were using was cumbersome. They were using aspirated psychrometry and things like that. And so it wasn't really a practical field tool. The other thing that was a problem was that they had to do these line fittings manually. Part of the reason for that is you can see on these lines, not all the data points fit on that line. They had to go through manually and work out which were the appropriate data points and which weren't. So I redesigned it. What was different about my one? For one thing, just more modern sensors, which were more accurate than what they had in the past. But the other aspect of my new system was how it processed the data to remove that manual process of examining the data. Theoretically, if your sensors are all inside the atmospheric boundary layer, then all the measurements at heights A, B, C, D, E should all fit on a nice straight line. That's what you'd expect to see. The reality is you're more likely to get data somewhere around a straight line. And the question that the authors previously and here you have to ask is, well, which data points are appropriate to be fitting a line through and which data points should I be throwing out? You don't really want to have to be examining that manually. So the solution approach that I took was each of these points has a region of uncertainty, a 2 sigma or 95% confidence interval uncertainty based on the measurement uncertainties in each of the vapor pressure sensor and the temperature sensor. What I would do is I'd fit the line through the data, and where the line was going through those zones of 95% confidence, I would keep that data, other data would be disposed. And I wrote software script that executed within the microprocessor to be able to do that automatically. So here's an example of each point has its ellipse of uncertainty, which is a result of having 2 variables with their own 95% confidence intervals. And here you can see the line of best fit goes through them nicely. Here's another example under different field conditions, and the line of best fit goes through all those ellipses just nicely as well. So all those data points can be kept. Here's one where you can see that the measurement at the highest set of sensors, point E, does not fit. And so the script would automatically just say, okay, I'll flag that, but for now I'll exclude that point E and I'll fit the line through the others and proceed with my calculations. The reason why point E is often we saw point E at the highest sensors not being fitted on was because that sensor was above the internal boundary layer, the atmospheric internal boundary layer. And this relates to the question of adequate fetch which is for the 2 height BREB systems that rotate, they had no way of knowing if those sensors were in the internal boundary layer or not. This approach does highlight the sensors that are outside the boundary layer. Here's another one. In this case, the sensors at A and E failed to sit on that line. And so the script, the logger would just go, we'll exclude those points and proceed with the line fitting through the other points. So how good was it? So this here is comparing 2 different, so comparing against eddy covariance, comparing 3 different, but I was comparing against eddy covariance and another micromet system that we've got under development at our organisation and BREB. And over the 7-day period, after 7 days, there was about a difference of about 1.8 millimetres between the BREB and the other systems. So roughly 0.2 to 0.3 millimetres per day difference. So this was a water-limited cotton crop with an incomplete canopy. So that any farmer would be happy with that. Another set of data, this is over bare soil. The blue rectangles show where it's irrigated or rained, and over the 2 weeks, after 2 weeks, there was only 4 millimetres of difference between the two systems. Pretty good. And this was over a fully grown, fully closed cotton canopy, and again, against the reference system, the Profile BREB compared really nicely. So who cares? I care because the eddy covariance systems were hard work to take into and out of the field repeatedly. We got over that very, very quickly. With this Profile BREB system, we were able to tie it into our other monitoring systems, and it could give us real-time data because all the processing was done in the logger, and it spat out really good quality data, but it also kept the raw data. We were able to identify the atmospheric internal boundary layer. That's kind of, I guess, more of an academic thing, but it's nice to know that what you are measuring is following the conditions that you require to apply this this technique. No moving parts on this Profile BREB system, which means lower power requirement. This draws milliwatts to run, and I was making measurements every minute. The automated processing as well inside the logger meant that the 32,000 measurements that I made were all processed automatically. And a big one was lower cost. So using research grade sensors, this was still less than $10,000, which is a huge cost, and that's including hardware, solar panels, batteries, and everything else, which is a huge cost reduction on eddy covariance systems. I developed this as a thing on the side during my PhD work, and then my supervisors got more interested in this than my actual PhD. So, and others have said, yeah, okay, keep developing it. We'll look to commercialise it soon. And she's easy to move and set up. Farm workers I designed it so that you could just fold it down if you're running a spray rig over the top, or you can easily just carry it out of the field without having to disassemble it. The downside of it, it doesn't measure carbon fluxes. I think it could work over natural ecosystems if they are low canopy, but for a lot of the big complex canopies that people here work with, it probably wouldn't work. And that's me. Thank you.
Hello everyone. Today my topic is about insights into the environmental drivers of soil carbon in the Australian regions. Imagine we could shrink down to the microscopic world. We will see that soil carbon is stabilized and protected through the association with mineral surfaces and locked within the microaggregates. Zooming out, the combination of aggregates, organic carbon matter, and pores between them create a complex habitat in soil. As we expand into the size of landscape, we will see that carbon stocks would rise and fall as the land changes. Taken to the continental scale or global scale, we would say that land use, climate, and time jointly control the carbon. Our research questions and hypotheses are there. What are the soil and environmental controls of soil carbon in the vast Australian regions? We have three hypotheses. Climate is not a main driver of soil carbon at smaller or transect scales. Soil mineralogy and landscape attributes influence soil carbon in the regions. The relative effects of drivers on soil carbon will differ with soil depths. We compile soil samples from 8 transects, and 6 transects were selected within 2 depths, 0 to 10 and 20 to 13. The acronym for each transect as follows: CYP for Cape York Peninsula, and 17 samples for the topsoil, 15 for the subsoil. MGD means Michelle Grass Downs. NK means Northern Kimberley. PIL means Pilbara. FLB means Flinders Ranges. MDD means Mary Darling Depression. The soil organic carbon measured with dry combustion and FTIR. And in this study, we will explore the transect-specific controls of soil carbon across Australian regions with small sample sizes and high-dimensional predictors. In this study, a comprehensive set of environmental variables as proxies for 6 factors: climate, vegetation, microbiome, and terrain, soil, parent material. These are the current best available data from TERN. And then we used a statistical model and physical knowledge to analyze this data. Differing from the Pearson and Spearman correlation learning to screen variables, with the highest correlation, we tried model-free feature screening methods, which evaluate variables based on some correlations like marginal correlation, distance correlation, Kolmogorov-Smirnov test statistics to select variables. To further select important features, we used palette regression methods such as NASO, SCD, MCP, or nonlinear methods such as rainforest and Bayesian model average methods. Finally, we provide optimized variable selection results with reliability test and other criteria. And then we used the partial least square SEM modeling, mainly because it can handle small size and model latent factors with few indicators. This heat map finger comes from a combination of model-free feature screening methods and palette regression methods. The color bar indicates the variable importance. The symbol of plus means the value selected variables. We can see that there is a high variability in the factors influencing soil carbon dynamics across transects. There is also a shift of K drivers from topsoil to subsoil. Taking Northern Kimberley as an example, NBR2 here means normal band ratio 2, albedo, soil fungi 1 are K drivers in topsoil. In subsoil, only NBR2 and indicator of soil mineralogy, PC1, principal components 1, are primary drivers of soil carbon. Moreover, factors like terrain and microbiome are most influential on topsoil Flinders Ridge transects, but terrain and parent material factors are key drivers in subsoil. This is the selected variables importance ranking for 6 transects within topsoil and subsoil. After using the model-free feature screening methods and exploratory factor analysis for final SEM modeling. For instance, for Cape York Peninsula transect, the fellow selected vegetation attributes of fraction of photosynthetic active radiation of absorbed radiation by vegetation elements, FPAR, albedo, and gross primary productivity, GPP, indicate they are the most important factors, while roughness and plain curvature show that top graph also has effects. For the subsoil of CYK transect, the primary factors imply that the vegetation attributes FPAR and parent material and TERN indices aspect and microbiome soil bacteria too are crucial for soil carbon variation. Overall, the vegetation and top graph are the primary drivers of variation of soil carbon in Cape York Peninsula transect. This is the SEM modeling at Darling Depression transect. For the topsoil of MTD transect, we found that parent material and vegetation biomass in the topsoil of MTD transect have significant impacts on soil carbon, with total effect values of 0.61 and 0.42 respectively. For the subsoil of MTD transect, we found parent material and vegetation greenness, landscape, and temperature all exhibit significant impacts on soil carbon. We also found that there is a significant negative EVI and soil carbon relationship and weak positive GPP and soil carbon relationship in subsoil. This is the takeaway. We proposed a robust and systematic framework for identifying important drivers of soil carbon with small sample size and highly dimensional predictors. The most important drivers of soil carbon are diverse depending on transects and soil depth. Generally, they are soil minerals like smectite, landscape attributes like DEM and terrain wetness index, vegetation productivity like GPP. The SEM modeling tells us that the relative effects from vegetation density and vegetation productivity on soil organic carbon are quite different. In transects where climate factors don't limit vegetation growth, more vegetation will contribute more carbon to both topsoil and subsoil. We would like to acknowledge the TERN for collecting the samples used for this study. We also acknowledge the Keaton Soil and Landscape Science Group for sample measurements. Without their contributions, this research would not have been possible. Thank you.
All right, thank you, the three of you. Those were some really interesting talks. We have some questions from the audience. And let's begin with the first to Lucas, asking, given the growth rate limitation regardless of CO2 increase, will there be a flow-on effects in some systems in terms of fuel loads and fire? Or any theories about this, for example, subtropical forests?
Hello. Yeah. So I think what I think is that we can expect increases in growth, more so in water-limited systems, and so not in the interior wet tropical forests, but let's say I think in savannas it seems reasonable. And in the savanna, you have the interaction of the C3 trees and the C4 grass. The rising CO2 should favor the trees. So I think increases in tree biomass can be, we have a good basis for predicting where we would expect to see those. And the other really important factor to mention is soil nutrients. So we do see a big growth response if we fertilize plants in the glasshouse. And so I think in particularly fertile soils, we would expect more of a CO2 stimulation of growth than in less fertile soils.
Thank you. The next question is for Simon. Who owns the intellectual property on your Bowen ratio energy balance system? Can others adopt the sensor? Who manufactures it other than yourself? Or maybe you do. And what is the adoption rate so far?
Well, the adoption rate so far is nil. It's still under development, and the IP is owned by the Cotton Research Development Corporation, and so they're funding me to take it to commercialisation. And then we'll find a partner to produce it. At this stage, we've probably got about another year of development work on it.
Mm-hmm.
It's demonstrated to be able to work quite nicely so far, but we want a lot of the work is for the back end to provide that data to the user in a much simpler way.
All right, thank you. And finally, well, not finally, but next, for Mingxi, and let me just say it's great to see you, Mingxi. Who analyzed the soil microbiome? Was it done at Curtin?
No, I just downloaded from the TERN website. SLST.
All right, thank you. The next question is for Lucas. Tropical trees at water-limited sites are more likely to drop their leaves when faced with water stress. How would you interact with the proposed WUE gains for photosynthesis?
Yeah, really great question. I think if the increase in water use efficiency leads to a slower depletion of soil moisture, then I could imagine the phenology might shift. But yeah, really good question. It's hard to make a prediction. We would need some excellent monitoring and measuring.
Great, thank you. The next question for Simon. I was doing Bowen ratio back in the 1990s, and we lost a lot of data for poor quality because of negative Bowen ratios. Now, one of the slides that you showed, the Bowen ratio is minus 0.3, and you didn't seem to have any problem with that?
No, negative Bowen ratios are fine, as long as you can assure the quality of the data. And so a lot of people will automatically throw out data between minus 1.25 and minus 0.75. And historically that's been because of the limitations of the sensor accuracies. The profile method, you don't have to automatically throw that data out. People who are familiar with Bowen ratio would know that when you get to close to a Bowen ratio of minus 1, you're getting onto risky ground. But
we were on risky ground. Next question for Mingxi. So it looked like one of your results was that vegetation effects were one of the larger drivers of soil carbon. So would this suggest that you can affect your soil organic carbon by, for example, changing crops?
Some transects, the vegetation is the major driver. Yeah, but in some tracks, the terrain indices are the major driver. Yeah, for the vegetation, I feel maybe changing the vegetation type is a good measure for carbon sequestration or carbon fixation.
Great, thank you. Oh, sorry.
Yeah, but it's just for the area climate don't limit the vegetation growth. If the climate limit vegetation growth, no, I don't think.
Thank you. That's a really good point. We'll move on back to Lucas, and the question for you is, you used facilities in Panama. Should Australia invest in more ecotron infrastructure?
Yeah, that would be wonderful. We have, you know, Australia has the FACE experiment at Hawkesbury, which I think is a great experiment. It would be fantastic to have an experiment in the tropical forest, but it is very expensive, and there's one that's recently started in the Amazon. I think that will provide a lot of really good data for understanding CO2 responses. So yeah, we could certainly use more facilities, but of course it has to be balanced against all the other research needs.
Okay. So I'm down to just 2 more questions for Lucas. And the first is, do you expect CICA to be constant for plants outside the tropics?
That's a good question. The tropics, I think, are in a sense simpler than higher latitude systems, because in the high latitudes you have the increasing CO2 concentration, but also a bigger effective temperature, and so you have longer growing season. You have potentially the mineralization of nutrients in the soil going faster as the temperature, as the soil warms, and so I think that it's slightly more complicated. But the general tendency is that CI on CA tends to remain the same, constant. Yeah.
Oh, okay, thank you. And the other one that I had was, did you see a change in transpiration with your water use efficiency?
Yeah, so we measured, the measurements we made, we tried to keep a more or less constant vapor pressure deficit. And so the transpiration, the stomatal conductance was a little bit lower, higher CO2, and so transpiration would have been a little bit less, yeah.
Okay, thank you all.
Thank you, Jamie, and thank you for that last session. So yesterday when we started the symposium, I was only limited to telling you where the toilets are. Today I'm allowed to say something far more exciting, and that is something about highlights of our symposium over the last 2 days. And I want you to think of an inverted pyramid. We shaped this symposium so that no matter how little you participated in, because I know some people have been in and out of sessions and some people have had to already go catch planes or buses and go home, but we started out with big picture type sessions and we gradually brought it down to more specific information. I think that's been a very successful formula, because no matter when you left, you had a very big picture view of what TERN is capable of doing. One of the main message that I got out of the 2 days was that people don't understand how far TERN has gone since it was first conceptualised. And our message these days is that we monitor ecosystems regardless of land use or land type. And so we obviously have to work on delimiting ourselves from that terrestrial part so that people recognise that we're also monitoring ecosystems that relate to coasts, ecosystems that relate to freshwater, and also to wetlands. Not so much at the moment, but with the next 5 years of TERN, which we're now entering, it's just ending the first month of our new 5-year term, we will be concentrating on things like that as part of our step change. Now, also with that inverted pyramid concept, I just want to highlight a few things that are at big picture type levels. So Hugh Possingham started us off with opening remarks to tell us that more people are becoming interested in nature. And you'd have to say that with the breadth that we've had, that we've been really delighted to see and to be exposed to, there is no limit to what everyone here is interested in and has brought to our attention. It's fabulous. The next one was something that Andrew Campbell, the patron of our Science Symposium, said. He said that we need to empower people where they are with the data that they need. And there were so many finer aspects of the sorts of data that we can bring to the people who need that data. And I think that one of the successes of TERN is it's making that data accessible and retrievable. We have a long way to go, but we are on the journey. And you remember Bronwyn Harch said, we're all on a journey, which brings me to her point, and that is that she said that some days we win, most days we learn. And I'd say that we're in learning credit at the moment after our 2 days here. We've banked a fair bit of learning that will do us over for the days that maybe we're not learning so much, maybe we're winning. I have quite a few things to do that happen at the end of a symposium. If you've enjoyed your lunch, if you've enjoyed the seamlessness of how the presentations have gone, the depth of the presentations, etc., then it's necessary for me to bring to your attention the people that have made that possible. So right up the back where there's a light shining in my eye are the AV people that have supported us. Thank you very much for making it so seamless. I think you'd all agree that you've been to such events where it's not been like it has been here. It's been fabulous. So thank you up there. Did you know that TERN provides student stipends to get students to come along and present at our symposium? We had 4 recipients of our stipends this year. We had Wes Cooper, Joe Owens, Laura Sotomayor and Mohammed Tagadosi. They were our 2023 recipients, but just keep that in mind as we start preparing for the 2025 symposium, that we're looking for students to come along and present posters or talks, and we're happy to support them to do that. Obviously, we had the delightful presentations by Hugh Possingham, Andrew Campbell and Bronwyn Harch, so we have to thank our keynote speakers, plenary speakers, and the chairs, the 8 chairs who kept you all in line as you did your talks and made sure that all the questions, so well done to the chairs, who I shall call out: Belinda Medlin, Megan Lewis, Tim Wardlaw, Matthew Luskin, Will Woodgate, Tim Clancy, Mike Grundy and Jamie Cleverly. Thank you very much for that. When you were having your lunches, morning teas and so on, I think it was a lovely atmosphere out there on the deck. And some of that was made possible because people put posters into our symposium. Thank you, poster presenters. And we also had a number of people who possibly, we were so surprised at their generosity, who provided exhibits and sat there throughout and talked to you during the lunchtime so that you had something to entertain you. So I'd just like to make a call out to the Australian Access Federation, the Australian National Fabrication Facility, the Australian Research Data Commons, Eco Commons, and ICT International. I think that was very nice of them to come, and we really appreciated their presence. And it wouldn't be possible if we hadn't had the depth of online and in-person presenters. We're just so indebted. We put out a call that we're having a science symposium. We have no idea who's going to respond to that, to come along and tell us what sort of science they're doing, and even perhaps that they may have been using some of TERN's infrastructure or data. It's been an absolute pleasure to meet you. I haven't said hello to everyone in person, but I have noted that you have been participating. So that has been absolutely wonderful. But really, the key to the whole thing that kept it all going is the team that's been beavering around, you know, about the ducks on water and the legs going madly underneath while everything goes serenely on the surface. So please put your hands up or stand up. Mark Grant. I've got to find my list. Peter Brady. Jaden Hausfeld. Nicholas Rakatapare. Yay. Mindy Gilling. Eleanor Velasquez. And Sandy Heggie. Absolutely fabulous. Now, I want to leave you on an absolute high as you go off. I wish you all very safe travels. Just stay put for a little longer because you may remember that there was a talk during our symposium that told you that if you are going to do something, do it very well and make it useful for a lot of things. That was the talk by Nicholas Rakatapare, telling you how to make use of the thing that is becoming very important in everyone's lives, and that's video, etc. And thanks, Nicholas, for bringing us the next little bit. We'll leave you on this note.